So, hello everyone. I'm Tanya. I'm one of the TAs assigned to the course Aircraft Design taught by Professor A.K. Ghosh. So, we will meet on Tuesday every week. We will briefly go over the concepts that you've studied in the lectures and solve a few questions that will help you solve the assignments that are due on every Wednesday. Okay, so we'll begin. This is just going over the few formulas that were introduced in the week 1 and week 2, week 1 mostly, week 1 lectures. So these formulas you should be familiar with. That is coefficient of lift, coefficient of drag, thrust. So there were several questions asked on the forum where they had doubts in the notations. So CL, that is this one, is coefficient of lift. CL naught is the zero lift coefficient. DCL by DL is the slope of the lift curve slope. So I will just, this is the CL versus alpha graph. So in this case, CL naught, can anyone tell me what CL naught will be in this case? DCL upon D alpha, this CL alpha is the slope. What is CL naught in this case?
The zero lift, the CL value of CL at zero lift angle of attack.
Yeah, so in this graph, what is CL naught?
Zero.
Zero, exactly. And this is characteristic of what type of airfoils?
Symmetrical.
Symmetric, yes. And when we move on to cambered airfoils, how will it be different? How will the graph move?
CL
Ma'am,
not
it will.
at negative angle of attack.
Exactly. So you will have a positive CL naught. So it ensures that you have a lift even at zero angle of attack. This is what a cambered airfoil does. Okay. Okay. So this is the equation for coefficient of lift. This is the drag polar equation, that is coefficient of drag. And this is the induced drag. This is the parasitic drag. Okay. Then we have the thrust equation. And this is for the steady cruise. So somebody asked in the forum, how is this thrust equal to this equation? So let's just try deriving it. So for a cruise flight, your conditions are lift equal to weight and thrust equal to drag. So you require the aircraft to, if it has to equal drag, this is the thrust required. So you can write, for this case, thrust required equivalently is T. Now, what does that mean? Thrust required equal to drag. Now divide both sides of the equation with lift. And since lift equal to weight, you can just write TR upon W equal 1 by L by D. And this gives us TR equal to W upon L by D. Okay, so that is how we came to this relation. This is the thrust required relation. Then our original equation, that is lift equal to half rho V square SCL. Here rho is the density at a particular altitude. So when this was another question asked in the forum repeatedly, the notation rho gives the density at a particular altitude. So when sir says rho at a given altitude, it does not mean the altitude, it means the density at that altitude. V is the free stream velocity, S is the wingspan, and CL is the coefficient of lift. So from this equation, we get V equal to this W by S wing loading upon rho CL. Rho again, I just repeat, it's the density at a given altitude. Now the same equation, if you plug in CL max instead of CL, that is here, you get CL max, you get the V stall. What is V stall? Can anyone tell me what V stall is? V, I said, is the free stream velocity. If you replace CL with CL max, what is V stall?
It is the minimum speed which is required to maintain the L equals to W.
Yes. What happens if you go below this speed? What if you try to fly your aircraft below the speed?
The aircraft goes down now.
Yes. Okay. So it will cross first stall. So alpha stall.
The angle of attack at which we saw the curve.
Yes. So physically, if you just take a cross section of the airfoil, at what point do you have this alpha stall? Why does this happen? You have an airfoil like this, and you have flow happening over it. So why does this stall happen?
because of flow separation.
Flow separation. Okay, so it's the angle of attack at which there is no enough lift produced to maintain the climb or the level flight. Okay, so there is not sufficient lift for you to continue the flight. So that is the angle at which stall occurs. Okay. Now this is just a comparison between the two cases that are discussed throughout the course, that is minimum drag and minimum power condition. Minimum drag or minimum thrust required is the one that gives you maximum range. When you minimize drag, you get a maximum range. And when you minimize power, you get maximum endurance. So this occurs when this L upon D ratio is maximum, CL upon CD, that ratio is maximum. That is when you have this minimum drag condition. So this ratio, when the CD is minimum, you get this ratio to be maximum. Similarly, for the minimum power condition, you have CL to the power 3 by 2 by CD. This term is the maximum for the minimum power condition. Now, in previous courses, we have seen that for the minimum drag condition or the minimum thrust required condition, coefficient of lift is related like this. CD naught and K come from the drag polar, that this drag polar equation. Okay, so if given a CL and you plug it into the drag polar equation, you get CD. This is, okay, should have written CD. CD for minimum drag condition is 2 CD naught. CD for minimum power condition is 4 CD naught. You will be using this extensively in the numericals. So with this, I think we'll begin the questions. So the first one is, which one is generally responsible to generate the lift of an aircraft? Discussed that the airfoil, if it goes at a particular angle of attack, it will stall. It will not produce the necessary lift to maintain flight. So we know that angle of attack is one parameter. Look at the other options: wing incidence angle, wing camber. So are all of these contributing towards generating lift?
Yes, all.
Yes, ma'am.
Yes.
All of these, ma'am.
All of these, yes. So the equation that we have is CL equal to CL naught dCl upon d alpha. This from here you get directly the angle of attack contributes towards lift generation. Now, when you on an aircraft, if you have set your wing at a particular angle, so this angle of attack is the angle of attack at the wing. So angle of attack at the wing would be angle of attack the craft encounters plus the wing setting angle. Okay, so again, wing setting angle directly contributes in this graph. Then what was the option? It was the wing camber. Yeah, so that is why you have this figure here. So if I have a flat plate at an angle alpha in the free stream, that also generates lift. So this FL is lift and FD is drag. That also generates lift. Now, if you have this shape, symmetric or cambered or whatever, if you have airfoil shape kept in the same free stream velocity at the same angle of attack, it again produces lift and drag. What is the difference between these two cases? Both of them produce the aerodynamic forces, that is lift and drag. What is the difference between these two cases?
There is less flow separation at the aerofoil
Okay,
because of its camber, but
yes,
there is a lot of drag in flat plate case.
exactly. So effectively what we see is that the lift generated in this case is less, and the lift generated in this case is more. And as you increase the camber, as we saw from the graph here, airfoil, it was this, and for cambered airfoil, it was graph. So it was CL versus alpha, CL versus alpha. So from this graph, we can see that cambered airfoil produces lift even at zero angle of attack. Right? So camber directly influences the lift generation capabilities. The flat plate, although it produces the same aerodynamic forces that are lift and drag, its quantity is different. Qualitatively, they are the same, but quantitatively, it's different. Lift produced here is much less than the lift produced in the cambered foil case. And the drag here, like he mentioned, it is much higher than the airfoil shape. The answer is all of these: angle of attack, wing incidence angle, and wing camber. All of them contribute towards lift generation.
Ma'am,
Yes.
ma'am, why the camber is not symmetrical?
Why cambered is not symmetrical? So even if you have symmetrical airfoil, it will produce more lift than the flat plate. Do you agree?
Yes, ma'am.
Yes. So this figure is just representative to show you the difference. But even if you have a symmetrical airfoil, I mean, there the camber is zero, right?
Yes, ma'am.
So even if it's zero camber, it produces lift. But when you increase this camber, when you have a positive camber, like in this case, you have lift produced even at zero angle of attack. But both of these cases, you can see the relation that it generates lift. That's all the question was asking. Okay. Was that your question?
No, I'm asking which is better, the symmetrical or positive, which will be better?
Okay, which is better? I will tell you. Okay, so cambered airfoil, like I said, even so when you're taking off your aircraft, even you have zero angle of attack at the point of takeoff, it will just start changing from zero. So even at the zero angle of attack, you have a lift generated in the case of a cambered airfoil. This is not present in the case of symmetric airfoil. Only when it starts changing the angle of attack do you get a lift. At zero, it is zero.
No,
Right.
ma'am, I was asking in case of symmetrical cambered, like
Yes. So this
there is a difference
symmetrical.
between the cambered from upper side and the lower side.
Yes, this is a cambered airfoil, right?
Yes, ma'am.
It's symmetrical. It's just this.
Yes, ma'am. I was asking for this one.
What was your question exactly?
Which will be better, this one or this one?
So this graph here is associated with the symmetric airfoil, and this graph is associated with this. Okay, so the symmetric airfoil does not produce lift at zero angle of attack. A cambered airfoil produces lift at zero angle of attack. So which one will be better? Even at zero angle of attack, you're producing lift. So isn't the cambered airfoil better?
Yes, ma'am.
Yes. Did I answer your question?
Yes, ma'am.
Okay. Okay. So moving on, induced drag for an airfoil is, so our drag polar equation is CD equal to CD naught plus KCL squared. Which term here is the induced drag?
CD naught.
CD naught.
Induced drag
KCL square.
KCL
square.
is the parasitic drag and this is the induced drag. Okay. So anyone tell me what the answer to the question will be?
Zero.
Finite but not zero, ma'am.
Okay, can you
Zero.
justify?
It will be.
Whoever told me finite but not zero, can you first, I'll ask you, can you justify your answer? I'm not sure who told finite but not zero. We can have a discussion here, so you can tell me why you think it is finite but not zero. No? Okay, so someone who told me it's zero, can you justify your answer?
Yes, ma'am. In an aerofoil, there is no standwise flow, which will create vortices, and then vortices are the main induced drag causing. So on an aerofoil, there are no vortices.
Okay. Someone else who said zero, do you have any other explanation? Are you satisfied with this one? A lot of people said zero. So anybody else has any other justification? Or are you okay with this? Or does anyone have another answer?
Ma'am, I think so it will be finite but not zero, ma'am. Because
Okay.
any aerofoil while during the flight, it will have some drag upon it, ma'am. And as we know, CD naught is parasitic, ma'am. So it will be largely dependent upon CL.
Yes. So this CL here this is capital L. Okay, I'm not sure if you've taken the aircraft performance course, but two coefficients, C small l and C capital L. This referred to for a 2D airfoil, right? And this was for 3D wing. So there was a difference between these two coefficients of lift. Okay, so our equation here, the drag polar equation here, has a capital L. Okay, so it does not depend on the 2D airfoil. So now let's see what induced drag is. So when an aircraft is flying through a free stream, the flow above the wing tends to move in this direction, this upper arrow, and the flow below the wing tends to move in this direction. The pressure below the wing is more than the pressure above the wing, which is why you have a generation of lift. So the direction of flow across the span is like this. Okay, so above the wing, it moves in towards to inward, and below the wing it moves outward. Because of which at the wing tips, there is these two interact and a vortice is generated, which is seen here, okay? So both of these are wingtips in this case, because if you imagine it to be not connected to a body, both of these tips have this generation of vortices, right? This is because the flow above and the flow below interact at the tips. So when it comes here, these two flows interact and you have a vortice being generated. Now when it carries across the flow, down flow, it pattern of vortices that go like this. That is in the trail of the wing. Okay. So if it is just an airfoil is what? It's a wing of infinite span, right? So there is no tip for an airfoil. If there is no tip in an airfoil, you don't have this vortice happen. There are no vortices for an airfoil. If there are no vortices for an airfoil, there is no induced drag. What is induced drag? Because of this interaction and because of the generation of this vortice, there is a change in the angle of attack. The angle of attack at the tip effectively changes. So your original airfoil, if I just take a cross section of the wing, lift and drag. This was drag, this was lift, and this was the angle of attack. But if you take it at the tip, due to this interaction and due to the generation of these vortices, you have a slight change in the inclination of L. And this change is the induced angle of attack. So because of these vortices, there is an component which renders it not perpendicular to the drag. And because of this change in lift, there is a small component of drag associated with it, which is the induced drag. This will not be there for an airfoil, because for airfoil, there is no tip and there is no downwash and there is no vortice generation at the tips. So for an airfoil, the induced drag will be 0. Okay. Is that clear, or is there some confusion?
Ma'am, could you explain it again?
Yeah, okay. So let me just erase all these. Okay. So when an aircraft is flowing, there is oncoming velocity in this direction. This is the free stream. This is oncoming velocity. So when it hits the flow above the wing, tends to move inward. When it moves across the wing, it tends to move inward. Similarly, the flow below moves in this pattern. This is because the pressure below is higher than the pressure above, which you know is what causes the lift. Now, if it was so if your wing had infinite span, generating, and if I take any cross section, it will be an airfoil that produces lift and drag corresponding to angle of attack. Lift and drag. But since it's not of infinite span, it is of finite span, it has a tip. So at this tip, this flow that coming from below tends to come above, and the flow that is coming from above tends to push it down. So there is an interaction between the two flows, what leads to these vortices. So there is a vortice generation here, which continues downward, continues in the trail. Because of this, when the flow changes here, at this point, the flow changes. It's not the same uniform pattern that was there throughout the other cross sections of the wing. At this flow changes, and there is a different angle of attack. So the effective angle of attack will also include this induced angle of attack term now. Because your lift is tilted. It was initially, this was the lift 1, this is the lift 2. It was initially perpendicular to drag, but now, sorry? Okay. So the lift is now tilted because of this new angle of attack at the tip. Because there is a change in angle of attack, the lift correspondingly there will be a change in the drag. This change in drag, extra drag that is coming because of the extra angle of attack at the tip is called induced drag, a small component. Okay, so that only occurs if there is this tip, because it occurs due to the vortices. If it is infinite span, there is no tip, and there will be no vortices. Hence, for an airfoil is nothing but a wing of infinite span. So for an airfoil, it will have no induced drag. The angle of attack will be same throughout the span. Yes? Does that answer your question?
Yes, ma'am.
Somebody has pointed out in the chat that everyone should mute themselves. Can everyone just mute themselves when we are discussing? You can unmute yourself when you have to ask a question, but otherwise, can you just mute yourselves? Let's hope they mute. Moving on. Among the following, which aircraft instrument measures the altitude and speed respectively of an aircraft? Somebody is unmuted and it's making noise.
Altimeter, pilot tube.
Yes. Can all of you just mute yourselves? It's becoming hard to hear.
Altimeter and pitot tube, ma'am.
Yes. So that is the correct answer. So altimeter measures altitude and pitot measures speed. So let's just go over the other instruments. What does magnetic compass measure?
The
Ma'am,
direction
it
of
measures the
heading.
direction.
Can you be a little direction as in?
Heading of the aircraft.
Heading, exactly. So let's just see the.
Ma'am, is it in the terms of degree from north?
Okay, I'm finding it really hard to hear. Can all of you please mute yourselves? I cannot mute you here. I'm not the host. It's I think it's coming from Dula Dino. Can you please mute yourself?
Important question.
Can you hear me, Dula Dino? I'm not sure if I'm getting his name right, but I think the noise is coming from his.
अरे 1 घंटे की बात है अरे भाई 1 घंटा अरे 1 घंटे के लिए जा
I'm
रहा
not
हूँ
sure what to do with this.
1 घंटा नहीं 1 घंटा ज्यादा नहीं
Okay. So the image here, this image, this is the magnetic compass, right? So it measures the heading. This is the reference of the aircraft for ease of access. So this is the magnetic compass. It measures the heading. It will turn according to at what direction you're going. Direction is also right. Some the direction, that's also right. But technical term would be heading. Another thing is gyroscope. What does a gyroscope measure?
Stability, ma'am.
Acceleration of the aircraft in axis.
CG, ma'am.
Gyroscope, acceleration, okay. But what is the quantity that we get? Like, so this is one of the gyroscopic instruments. From this, can you try to figure out what it measures here?
Our horizon.
Yes, horizon, correct. So what is this angle? So here it is flying steady. Here it is turning. So what angle changed here?
Roll angle. It is banking.
Roll angle. So yes, gyroscopic instruments measure the attitude, the roll, pitch, yaw. Okay. So these instruments measure those quantities. These two red boxes are the correct answer. It's altimeter and tube. Okay, the noise is really disturbing. Dula Dino, can you hear me?
Yes.
Can you please mute yourself?
Okay.
Yes. And Saurabh. Yes.
Ma'am, I'm having a doubt, ma'am.
Yes.
Ma'am, can we say that gyroscope even says about the stability of the plane?
Stability of the plane is measured using the stability derivatives, right? So what is stability? Can you tell me the basic simple definition of stability of any system?
When a thing steadily goes or flies, ma'am, without getting any turbulence.
Okay, so that's not quite right. So stability is, equilibrium points, right?
Yes, ma'am.
Okay, so equilibrium points are the points where the sum of all forces and moments are 0. Okay, yeah.
Yes, ma'am.
Okay, so stability is the tendency. When you say static stability, it is the tendency of the aircraft to go towards the equilibrium point. If you just say stability, it tells you a measure of whether it will go back. So if an aircraft is flying in a steady flight and it is disturbed, okay, just take this typical example that you begin with in all the classes. So you have a ball here and a bowl, and if you disturb, this is an equilibrium point, right? It's not moving. If you push it towards this side, that is, if you subject it to some disturbance, it will come back to its equilibrium after a few oscillations, right?
Yes, ma'am.
Yes. So stability is defined as the ability to come back to its equilibrium point. So the quantity that measures these parameters as far as an aircraft is concerned and as far as static stability is concerned are your stability derivatives. Stability. Okay, so stability derivatives are what? Cm alpha, Cn beta, these quantities. Cm alpha is dCm upon d alpha. Okay, so these are the quantities that measure the stability. These are the quantities that tell you whether an aircraft will come back to its equilibrium if you subject it to a disturbance. So gyroscopic instruments just measure the attitude. What are the attitudes? That is theta, that is pitch, yaw, and roll. Right? So the gyroscopic instruments just measure these. It does not give you an indication towards the stability. Stability comes from the stability derivatives, not from the attitude measurements. Okay?
Yes, ma'am.
Ma'am, what does the third angle determine? Is it the angle of bank?
Which one? The one that I've written?
Yes, ma'am.
Okay, so this is pitch, this is yaw, and this is roll. So the angle that's indicated here, this is 5.
Is
Okay?
it same as called as bank angle of bank or bank angle?
Yes. There is a slight difference which we will come to through the course, but as of now, you can assume it to be the same. When you bank, you roll.
Okay.
What happens is if you roll right, you also have a yaw component that occurs. You can't just roll, right? So you'll also yaw. So all of those quantities contribute towards banking. We will come to that later on in the course, but so as of now, you can take it to be the same.
Sure, ma'am.
So this is the equation for altimeter, and these are the equations for the Pitot tube. Pitot tube follows the Bernoulli's principle, which gives you the speed. You know the stagnation pressure, you know the static pressure, density, you know at the given altitude, and you can find the velocity. That's how the Pitot tube measures the velocity. The altitude measured by the altimeter is again with taking pressure terms. This is for the troposphere, and this is for the stratosphere. Okay, so here the difference is that there is a rate of change of temperature involved here, that is alpha. In a given region of the stratosphere, it's not the entire stratosphere. It is from 11 to 20 kilometers. There is no change in temperature, so that term is missing here. So these are two equations by which we measure the altitude using pressure measurements. Okay. So next question is, if the weight of an aircraft is 1000 kgs and lift to drag ratio of an aircraft is 15, what is the thrust required in newtons at cruise condition? So first of all, what are the quantities given to you? You have weight is 1000 kgs and you need to measure it in newtons. So you immediately just write down 9.81. Okay. Then you have lift to drag ratio, which is 15. They've asked you thrust required. And they've asked you at level cruise. Cruise is lift equal to weight, thrust equal to drag. Now in the first slide, we've seen the equation for thrust required as, can someone recall it? Thrust required is?
Ma'am,
Weight
W by
upon
L by D.
L
W
upon
by
D.
Correct, correct. If at any point you forget this, we have done the derivation. It's fairly simple. I'll just do it again. thrust required equal to drag for a cruise condition. This is equivalent only for cruise condition. Divide both sides by lift. Since lift equals weight, you have thrust equal thrust by weight, 1 upon L by D. And from here it follows the thrust required is W upon L by D. Okay. So now I just plug in the values here, which is 1000 into 9.81 by lift upon drag ratio is 15. So how much is this value? Can you just calculate
B, ma'am.
how much?
B option 658.
Is it 658? Can somebody else confirm? Is it 658? I'm just going to go with that assumption, okay?
Oh, ma'am, 654 it is.
Ma'am, 654, ma'am.
Okay, okay.
650.
Correct option is A. So I've just given you equation here. It's the same thing that we've done. Next question is the stability producing component for an aircraft. We just now discussed what is stability. Can someone remember the simplest definition for stability? What is stability?
The initial tendency.
The
of the
ability
aircraft
to body to come in its equilibrium position.
Yes, the ability for a body to come to equilibrium position. And in aircraft case, we have static and dynamic stability. Static is the initial tendency to come towards equilibrium. Dynamics will actually tell you whether it will come to the equilibrium given a particular period of time. So over time, will it come back to equilibrium is what dynamic stability tells you. So any guesses as to which component contributes towards stability?
Ma'am, may you please explain the difference again between static and dynamic?
Okay, just a minute. So static is tendency to return to equilibrium. Okay. Dynamic is over time will aircraft return to equilibrium. So static stability does not tell you whether it will come to equilibrium or not. It's just the tendency. Does the aircraft show any inclination towards returning towards the equilibrium point? Dynamic stability is what tells you whether it will achieve that equilibrium or not, given a time. So you have, suppose this is your equilibrium state. The aircraft is initially flying at this state and you subject it to some disturbance. So it comes here. So over time, will it come back to your equilibrium or not? So this is a dynamically stable system, right? It's coming back to equilibrium. So there may be some systems that if you disturb, it will just diverge further and go. This is unstable, this is stable. So this dynamic stability is what tells you this behavior. So this is time and this is whatever state you're measuring. State and time. So dynamic stability, the component of time comes into picture. So over time, will it achieve equilibrium? Static stability just tells you whether the aircraft has some component that will try to bring it to equilibrium. It does not tell you whether equilibrium will be achieved or not. Is it clear? Is it clear?
Yes, ma'am.
Okay, yeah, okay. So any guess which component will
Tail, aircraft tail.
Tail, yes. So in the previous course that I'm hoping you would have done, we have studied the stability and control course. We have studied these equations. So the equation for pitching moment coefficient, M is pitching moment, and this is the pitching moment coefficient. Rest of the terms have the similar notation as CL and CD. So this is the equation for pitching moment coefficient, and the condition necessary for static stability is that dCm upon d alpha should be less than 0. Okay. The other condition that we have is Cm naught should be greater than 0, but that is not contributing towards any static stability. For static stability, you need to remember that dCm upon d alpha is less than 0. Now we look into the equations of the wing contribution and tail contribution. So the Cm equation, pitching moment coefficient equation for the wing is given by this equation. Now this term contributes towards, if you equate it to the main equation, this contributes towards what? Okay,
CM.
Cm naught, exactly. So this is the Cm naught contribution of the wing. and this is the Cm naught contribution of the tail. This is the Cm alpha contribution of the wing, and this is the Cm alpha contribution of tail. So now here you see you need Cm alpha to be less than 0. Now this term is positive. This alpha wing that doesn't come in Cm alpha. So this term is positive. The sign of this entire Cm alpha is governed by this term. So now for a typical aircraft, if you have the wing here, and suppose you have a tail here, whatever. So this is the CG. Okay, so this is the CG of an aircraft. This XCG is the distance from some reference point to CG. So let's take our reference point to be here. So this distance is XCG. This point is CG. Then the next term here is XAC wing. XAC wing is the aerodynamic center of the wing. So aerodynamic center of the wing is most often at the quarter chord point of the wing. So that is here, XAC wing. So this term will be positive or negative. XCG is this, XAC is this. So the entire term, this XCG minus XAC, will be positive or negative?
Positive.
Positive. So the Cm alpha contribution of the wing is overall positive. So it doesn't contribute towards stability. Now we see the tail. This Cm alpha of tail, let's see the sign. So VH is positive. This is positive. Cl alpha is positive. And what is VH? Does anyone remember? This is the tail volume ratio. What is this VH? Has anyone taken the stability control course? What is VH? It's called the tail volume ratio, horizontal tail volume ratio. What is it equal to? Okay, let me just write it down. It is area of the tail, moment arm of the tail, upon area of the wing, mean aerodynamic chord. Area of the tail, area of the wing, mean aerodynamic chord. This moment arm, LT. What is LT? Suppose this is the AC of the tail. So this is XAC tail. XAC tail minus XCG. So that is the moment arm, right? So what happens is this entire term becomes negative. Cm alpha tail is less than 0. So this contributes towards static stability, right?
Yes, ma'am.
Yes. So that is why you say that the aircraft tail is what is the stability producing component of the aircraft. Okay.
Ma'am, that entire term becomes negative, or that contributes to the negation of that equation that we've been given over there?
The entire term is negative. So as long as
If the entire term becomes negative, then we
Yes.
have a minus sign before that. So that will ultimately become positive.
the
Will it be
entire
added?
term okay, I think I
Will
made a
it
mistake. Be positive.
Will it be added, or will it be subtracted? That's
Yeah.
what my question was.
I think I made a mistake here. This will be positive. Okay, no. Let me just,
Could you just cross check that for a moment?
this is minus. This VH is this LT. LT is the moment arm, right? It's a positive quantity. Do you agree?
Yes, ma'am, absolutely.
Yes. So this including the negative sign becomes negative.
Oh, okay, then it will be subtracted of that mean term, right?
Yes. So the entire, this whole thing becomes Cm alpha tail, and that is negative.
Then it makes sense completely. Thank you so much.
Yes. Okay. I think it was confusing the way I explained, but I hope it's clear now.
Yeah, ma'am, it's clear.
Thank you. So moving on. If aircraft is in static equilibrium, it means equilibrium is the point where sum of all forces and sum of all moments is 0. So if the sum of all forces and moments are 0, you don't need to. So what do control surfaces do?
Change the movement.
Ma'am,
Or-
stabilize the aircraft.
Stabilize the aircraft. So control surfaces, when you deflect the control surfaces, it changes the effective angle of attack at those surfaces, which produces moment that counteracts the disturbing moment. So it contributes towards stability. So if the aircraft is already in a static equilibrium state, do you have to deflect any control surfaces?
No, we don't.
No, ma'am.
So this
No,
first
ma'am.
option is the correct one. So if it is flying in equilibrium, you don't require it to come back to equilibrium. So the aircraft controls are 0. Now, if it is subject to a disturbance, then you may or may not have to deflect the control surfaces. Okay, but if it's already in equilibrium, you don't have to do anything. Next question. If the weight of an aircraft is 1000 kgs, the weight of aircraft is 1000 kgs, lift to drag is 15, wingspan is 10, mean aerodynamic chord is 1 meter, and the aircraft is flying at a speed of 50 meters per second. What is the lift coefficient at cruise? So again, we'll just write down the data given to us. Weight of an aircraft is 1000 into 9.81. Then you have lift to drag ratio. This is newtons. Lift to drag ratio is 15. Wingspan. What was the notation for wingspan?
B.
S.
S. S is 10 meters. Mean aerodynamic chord. What was the notation?
B.
C, right? Chord. Mean aerodynamic chord. So it was 1 meter. So in your aspect ratio, which is B square upon S, B is your, what is B here? S is the span. What is B?
Ma'am, actually,
Length.
B is the span.
Is B the span? Okay, then I think I'll have to look into this. Okay. Okay, I'll have to look into this. I'm sorry about that. So let's just continue with this. I'll look into this and get back to you, okay? So V is 50 meters per second. Now they've asked you what the lift coefficient at cruise is. Again, you start with cruise conditions. Lift equal to 8. Okay. So how do you proceed from here? Right. So you have CL half rho V square SCL equal to weight. And they've asked you to find out the lift coefficient at cruise. So that is 2W upon S by rho V square, right? Substitute these values. What do you get? Substitute these values, what do you get? This is V. The answers come up in the chat box. Yes, B means span. I just looked into it. I'm sorry about that. Right? So the answer is, these are the equations that I've used here. What is the answer? Why? Who's getting 5.2? A few answers are 5.2. I'm not sure how you've arrived at that. Can you try calculating it again? I'll just do it once more. Just try calculating it again. A couple of people have got 5.2. How did you get that?
It will be 6.4, ma'am.
Yes. 0.64, right? 0.64. So coefficient of lift
Yes, ma'am.
lies in these values. It cannot be 5.2. So just verify your answers when you get such unrealistic cases. It's typically in this range, right? 0.6. It's like that. Exactly. 0.64. So you get 0.64. So coefficient of lift, it's not the lift, it's the coefficient of lift. So when you get large numbers like 5.2, you can verify that you've made a mistake somewhere. You can just check again. It comes in these decimals, right? 0.64, that range. Next, the temperature ratio at 16 kilometer and 12 kilometers. So before we get into this, we'll just look into the standard atmospheric model. This is the standard atmospheric model that we need to look into before we make any calculations regarding the flight of an aircraft. So in the tropospheric region, that is from 0 to 6 kilometers, in that range, your temperature reduces as the altitude increases. So in that range, as altitude increases, temperature reduces. Remember, I had told you there was an alpha term in the altimeter equation. That is due to this reduction, rate of change of temperature with height. So there is a reduction in temperature in this first 6 kilometers. Then from kilometers 6 to 12, the temperature is constant. So this is the first, that is from 0 to 6. Next, as height increases, temperature remains constant. That is from 6 to 12. Then again from 12 to 31, 12 to 31 kilometers, there is an increase in temperature as the altitude increases. So this is all we need to concern ourselves with so far. So as far as the aircraft flights are concerned. So now let's get back to the question that says, what is the temperature ratio at 16 kilometer and 12 kilometer? So they basically asked you T16 by T12. What is this ratio? So at 16 kilometer,
It will be same M1.
Yeah, it will be same. Okay. Is there some error in this graph? It should be 1, but
Ma'am, I think you are reading miles as kilometers. That's why.
oh yes, yes, yes. Okay, yes. Thank you, thank you. Thank you for that correction. So it's from 0 to about 11, and this will be from 11 to about 20. This will be from 20 to about 50. So this ratio, temperature in this region remains the same. So this ratio will be 1. Thank you for the correction. I was making a mistake there. So the next question is, aircrafts can be classified based on. So classification of aircraft is done in various ways. So all of these are different modes of classifications. Some of the other ones are, I'll just go through all of them. So based on the total weight of an aircraft, you have lighter than air aircrafts, heavier than air aircrafts. Lighter than air example would be, heavier than air is almost all of the regular aircraft. What about lighter than air?
Airships,
Man, gliders, ma'am.
Balloons.
airships, balloons, aerostats.
Yes, correct, great. Depending on the size of the aircraft, we have these categorizations and many others, but these are the major ones. You have micro airplane, double-seater, single or double-seater. You have medium with 50 passengers, large with 400 passengers, and cargo, the large cargos. Any example of the cargo aircraft that you know?
Antonov.
C-17 Globemaster, ma'am.
Hercules.
Yes, okay, great. Depending on the mode of operations, you have commercial, non-commercial, military, all of those categories come depending on the modes of operations or the missions that they fly on. Such categorizations are there. Then another major classification is speed. So subsonic is less than Mach 1. Transonic is in that region between where it just becomes supersonic. So it is about 0.8 to 1 Mach. When it crosses Mach 1, it is supersonic. And when it crosses Mach 5, it's hypersonic. Hypersonic vehicles, any idea? When it crosses Mach 5, what would be a typical example of hypersonic vehicles?
Ma'am, SR-17.
Space shuttle.
There's no
Space shuttle,
SR-17.
yes.
It was SR-71.
Yeah, SR-71, it's still in the
SR-71 was
surface.
supersonic, 3 Mach.
Yeah, supersonic. It was about maximum was 3.3.
NASA's F-15 was hypersonic, 6.7 Mach.
Okay, I'm not sure about that, but yes, shuttles, spacecrafts, all of those are hypersonic vehicle examples. That's greater than Mach 5. Not sure about the example that he said. I will certainly look into it. Then you have classifications based on type of engine. You have propellers, turbojet, turbofan, ramjet, and there are scramjets, supersonic ramjets, or scramjets. So you have types of engine classification. Then depending on number of wings. So you can have monoplane or biplane or triplane. That is how many pairs of wings you have. Single pairs of wing, that typical aircraft that we see, that is monoplane. If you have 2 sets, you remember the Wright brothers aircraft, you have multiple sets of wings. So that would be biplane, triplane so far. Then depending on different arrangement of wings. So you have your standard wing is this, right? So if this is the front view. So this is called mid wing. So if you have the wing here, you have low wing, and the other thing is high wing. Then since due to stability concerns and all of that you might have studied in the stability control course, for a low wing aircraft, you have an angle that is introduced, dihedral angle. Then you have something known as sweep. So if this is the top view, a typical aircraft has a rectangular wing like this. And if you introduce a sweep angle, it's something like this. Right? So this dihedral angle, and this sweep contribute towards directional and longitudinal stability, not longitudinal, directional lateral stability. So you would have studied that in the stability control course. So depending on all these types of wings or the number of wings, you have several other categorizations. So the answer to this question is all of these. Aircraft is classified based on all of these categories. There are some questions in the chat box. Okay. Yeah, missiles are also, I think, hypersonic, right? Next question is, during a flight, due to the passenger's movement, the center of gravity of the aircraft moves away from neutral point. Due to this, the elevator angle required to trim the aircraft will be. So what is trim?
Trim is to maintain level flight in non-stable condition.
Okay, so trim is just the same as equilibrium. Okay. One of the equilibrium conditions is the level flight that you've said, lift equal to weight, thrust equal to drag. But trim just means equilibrium, where the sum of all forces and sum of all moments is 0. So that is your trim condition. So do you remember from the stability control course that there was a particular elevator angle that you deflect to ensure that your aircraft is trimmed? So there was the relation between this elevator angle and the CL, right? I'll just show you that graph. This was the graph between delta E trim. Delta E was elevator deflection. What is elevator?
Control surface on horizontal stabilizer.
Yes, control surface on the horizontal tail. Yes. So any idea what it controls, like what
Pitch
attitude
of
it
the
will-
aircraft.
Correct, absolutely correct. So this is the relation between this delta E trim, that is the amount of elevator deflection required to trim the aircraft at some given CL. And this is the CL, right? So it's between delta E trim and CL. And the equation is given here. So this is the y-intercept and this is the slope. So in our question, they have mentioned terms like neutral point and CG. So this is the place that we'll be focusing on. So here, where the slope is 0, that is when CG equal to neutral point. So when the CG of the aircraft is at the neutral point, you have this. You have no slope in this equation. As the CG moves further away from neutral point. So if you have neutral point here, and if you have CG1, CG2, this would be CG1, CG2, CG3. So as you move away from the neutral point, the slope decreases. Right? At this point, it is 0. After that, it keeps decreasing. Now, the question they have asked is, during a flight, due to a passenger's movement, the center of gravity moves away from the neutral point. So
It doesn't specify ahead or behind of neutral point.
So if it goes behind neutral point, it will not be a stable aircraft.
Yes.
Usually we do not allow that. So, okay, yes, it is ambiguous. It should have specified ahead or behind. It goes after. But let's just presume it's a stable aircraft, okay? Okay. So initially, if we take, if the CG was at CG1, and then due to the movement, it moves to CG2. And now they've asked, how will the delta E change? So suppose at CG1, suppose this is the CL at which we want to trim. CL trim. Let's just draw a line there. So at CG1, your CL delta E trim for CL trim was here, right? Now for CG2, for the same CL trim, delta E trim has become this. So did delta E trim increase or reduce?
Reduced, ma'am.
Reduced. Okay. So that is the answer here. So when the passenger, when the CG moves away from the neutral point, the delta E trim reduces. Why? Why does it reduce? So the measure of stability, measure of static stability, there was the stability margin, right? Static margin, which depends on this term. So larger the static margin, so this term xnp minus xcg is a quantitative measure of static stability, longitudinal static stability. So larger this term, larger the stability of the aircraft. If the aircraft is more stable, you require less control surface deflection to stabilize it. So when the CG moves away from the neutral,
Could that also mean that the larger that term, the longer the aircraft?
not necessarily. What if you have a heavier component here?
Then it'll work.
Payload. Yeah. So, so larger the term, it is more statically stable. It requires less control surface deflection to stabilize it. But at what cost is this achieved? The maneuverability reduces. So it takes, the pilot puts in more effort to maneuver the aircraft. So an optimization has to be performed here to design the aircraft, which we will be studying over the course of the following weeks. Okay. So when the CG moves away from the neutral point, this term increases and the delta E trim required is less. You need to deflect the elevator less to stabilize the aircraft. Okay. So next question is the primary control surface used for angle of side slip control of an aircraft.
Rudder.
Rudder. Okay. So here is one correction in this question. This question is not completely right. So this is a point where there's a lot of confusion. There are two angles. You have the yaw angle and the side slip angle. Can anyone tell me what the difference is? Looking at the figure, what is the difference between these two angles?
Which two angles? ma'am?
Ma'am,
Yaw and
first-
side. Yes.
Ma'am, in the first figure, the plane has moved towards its
Yes. Yes, you're right. You continue.
Ma'am, your angle is given with reference to the degrees from the north.
Yes. And side slip, what is side slip?
Side slip could be-
Aircraft is drifting outwards if we consider it in a turn, respected to the relative wind.
Okay. So this side slip angle is somewhat analogous to the alpha, angle of attack. So angle of attack is the angle. So if your aircraft is in this way, if it's a side view, sorry about the figure. So if this is the angle of attack, it is the angle between, what is the angle of attack? Angle between?
Chord line
Chord line and relative
airflow.
airstream.
Yes. So chord line and relative airstream. This is angle of attack. Now, this analogous term in the top view is the side slip angle. So your initial velocity, free stream velocity was coming in this direction, but due to a gust, it has moved in this direction, which has introduced a side slip quantity here. And to stabilize the aircraft, we need to give it a yawing moment. So what we are effectively controlling here is the yaw angle. So your aircraft cannot control the side slip. Side slip is due to the relative airflow. So the question here is wrong in that sense. The primary control used for angle of side slip control. Angle of side slip cannot be controlled. What you can control is your attitude. Your attitude, I repeat again, is theta, phi, and psi. This is the pitch. This is the roll. And this is the yaw. These are the three angles that you can control. You cannot control alpha or beta because they come by virtue of the relative airflow. So this question should have been primary control used for yaw control. Angle of side slip is not the same as yaw. So you introduce a yaw or a yawing moment to negate the effect of side slip, but you cannot control the side slip angle. Is that clear? But you're right, rudder is the control surface that controls this
Yes, ma'am.
yaw direction, that is angle across the z-axis. So your rudder is the right thing, but this term is wrong. It should have been yaw. You cannot control alpha or beta. You can control only the attitude, that is pitch, roll, and yaw, phi, theta, psi. Aircraft longitudinal stability depends upon. We just looked into the equation and we have concluded that it depends on the tail. Right? For static stability, you need the Cm alpha to be less than 0, and that comes in only through the tail. What component of the tail contributes towards longitudinal static stability? Let's look into that equation again. Okay, so tail contribution equation was this, and this contributes towards Cm naught, and this entire thing, including the negative sign, contributes towards Cm alpha. For stability, we require Cm alpha to be less than 0. So what term here is given in the options? It has to be one of the terms that are given here. So what
It
is
is tail moment arm, ma'am.
tail moment arm? And where is it in this equation? Where is it present? It is
Theta.
yes, VH. What was VH?
VH was the ratio, ma'am.
Volume,
So
I think.
it is the tail volume ratio. It is given by area of the tail. Oh yes, so S is the area of the tail. I was wrong earlier. B was span. I'm sorry. So this is the tail volume ratio, which is given by ST. That is the area of the tail moment arm, area of the wing, and chord of the wing. Right? So this is tail volume ratio. So this moment arm term appears here. Do not confuse this tail area with control surface area. Control surface area would be SE, that is area of the elevator. This here is the area of the entire tail, not the control surface area. Okay, control surface area would contribute towards controllability, not towards the stability. Stability term is tail moment arm. Okay, what is eta? Somebody had mentioned that tail moment arm is coming in eta. So can someone tell me what eta is? This quantity, what is it?
Ma'am, eta is efficiency, ma'am.
Yes, what is it equal to? It is the efficiency factor, you're right. Eta is velocity observed at the tail times the free stream velocity. Why is the velocity observed at the tail different from the free stream velocity?
Because of downwash or
Yes, you're absolutely right. And here in this entire equation, what are the terms that indicate downwash?
IW.
Sorry, what? I couldn't hear you. Can you repeat it?
IW, I guess it is.
IW. Okay, let's just go over each of these terms in this equation. So VH we have discussed. Eta is the tail efficiency factor. CL alpha tail is the lift curve slope of the tail. IW is the tail setting angle of the wing setting angle, right?
Oh,
So
sorry, ma'am. Yes, epsilon naught it is.
epsilon naught and this dou epsilon naught by dou alpha are the terms that are indicative of downwash. So your entire downwash angle will be epsilon naught. So will be epsilon naught plus dou epsilon by dou alpha into alpha wing. So this is the entire downwash angle. Okay. This is the entire downwash angle. Any other term that we forgot? Yes. IT is the tail setting angle. IW is wing setting angle and IT is tail setting angle. All the other terms are clear, right? Does anyone have a doubt in this equation? Continue.
No doubt.
Is there a question?
No, ma'am, no doubt.
Okay, let's move on. During a maneuver, lift is 5 times the weight of the aircraft. If the trim velocity at cruise was 80 meters per second, what will the velocity during this maneuver be? So what it says is, so during trim, where was it? Cruise, what was the condition for cruise? Lift equal to weight, and the velocity at this condition will be half V square SCL equal to weight, and velocity will be root over 2W upon S by rho CL. This is given as 80 meter per second. Now what does it say? Now what we have to change here? This is the first velocity. In the second condition, what happens?
Lift increases 5 times. Or
Lift
the weight we can.
times the weight. So lift becomes 5W. So in the V2 will be root upon 2 into 5W upon S by rho CL. So that will be root 5 into, I'm just splitting the terms inside the square root, by rho C. Now this term is nothing but the original V, which was root 5 into V1, and that is 80 meter per second. So root 5 into 80, right? So this is the correct answer. Do you agree with me?
Yes, ma'am.
Yes, ma'am.
Yes.
Yes, ma'am.
So this, I've just written down the equations here. So the correct option is this one. Similarly, look into this. Try solving this on your own. During a mission, food packets are dropped. As a result, the weight of the aircraft is reduced to 70% of its initial weight. What will be the new stall speed if initial stall speed was V? So if V stall initial, that is, what is the equation for V stall?
2 times W by S
Yes.
divided by rho
CL.
CL.
Yeah. It's CL max. Okay, don't forget that. Rho CL max. So this is your V stall. In the next, let's take it as V stall 1, or let's take it as VS1. Okay. Oh, it's already given as V. Okay. So now in the new condition, that is V stall 2, what changes inside this square root? What has changed? 2?
Into 0.7.
W is reduced.
Exactly.
0.7.
Weight has
0.7
changed.
W. Exactly. CL max, which gives you square root 0.7 into V, which is again this answer, right? So it's similar to the previous question. Next question is, okay. Generally, lift to weight ratio during takeoff will be
Greater than 1.
Greater than 1.
exactly. So lift is greater than weight. That is what ensures takeoff. So it has to be lift by this has to be greater than 1. Correct. For a cruise, what will it be?
Equal to 1.
Equal to 1.
Exactly. Will it ever be 0?
No, ma'am, the aircraft will fall down.
If it's 0 technically, then that means that lift is 0, no? That is not
Yes.
possible.
It's not possible. Correct. Okay. So next question is the drag polar of a propeller driven airplane is given by this equation. Drag polar was CD naught equal to CD naught plus KCL squared.
11.
Okay, now let's just try solving this. So the values that are given here, they've asked you to find out the lift to drag ratio at minimum power condition. What was the minimum power condition? CL was what at minimum power?
Under root 3 CD naught by K.
Under root 3 CD naught by K. So in this case, it will be under root 3. CD naught is 0.05 and K is 0.03. What is this value? Can you just calculate? and tell me?
2.236. 2.236.
6. Okay. And CD for minimum power was? What was CD for minimum power?
4 times CD naught.
4 times CD naught. And that value is 4 into 0.05, which is?
0.2.
Now the lift to drag ratio is nothing but the coefficient of lift to coefficient of drag. 2.236 upon 0.2. which is
11.
that is the correct answer. So I've just written down these. This I took it from the table that we had discussed initially. These are the conditions for minimum power. So CL upon CD, CL to the power 3 by 2 upon CD will be maximum. CL and CD will be this. Next, they've asked you at maximum range. Maximum range corresponds to the first one was minimum power, which
CD
gave
naught by K, under root CD naught by K.
okay. CL equal to the root CD naught by K, but what was the main category of this? Like minimum power required was maximum endurance. So maximum range was what? What is the analogous corresponding term? It's the
Minimum thrust.
minimum thrust required, minimum
required.
drag. Yes. Okay. So can you give me this value? CD naught is 0.05 by K 0.03. What is this value? Can you just calculate it?
1.29.
1.29.
1.29. Okay. What about CD, which is 2 CD naught, which is 2.5.1. And again, the lift to drag ratio is
13 at 12.9.
12.9. That's it. Again, I've just written down the relations here. Now the question is the ratio of the aerodynamic efficiency at minimum power and the maximum range condition will be. What is aerodynamic efficiency?
CL by CD.
CL by CD. Okay. So we just take the ratio of the previous two cases. CL upon CD. CL upon CD. This was for minimum power and this was for minimum thrust. What were the two values? This
11.8 and 12.9.
comes to 0.866. This is something that was derived in the lectures analytically. Do you remember this? This ratio will always be this 0.866 for any aircraft. For not any aircraft, for the propeller driven aircraft. Okay. This was given, this was derived in the lectures analytically. So for a propeller driven aircraft, this ratio will always be 0.866. The purpose of this question was to just show you that angle of attack in degrees of the same aircraft for maximum range condition. So now they've given you the lift curve slope. So let's just draw this. They've given you CL alpha and they've given you alpha at a lift equal to 0. So the curve will look something like this. So it's a cambered airfoil, CL alpha, and this value is -1 degree, and the slope is given to you. So for our CL equation, CL is CL naught plus DCL upon D alpha into alpha. So we have this value. We need to find out alpha. And we know the CL for the maximum range condition. We just got that value. So what is missing? CL naught. How do you find out CL naught from this graph? What is CL naught? You have this value. You need to find out this value. This is CL naught, right? So what do? You do 0 minus of -1 upon CL naught minus 0. Right? Sorry, Bala. Upon CL alpha, right? Okay, no. CL alpha is the slope. So it's CL alpha into this value. What is this value? CL alpha into this value will give you CL naught?
-1 degree.
0 minus of -1.
-1.
Right? CL alpha is 0.1 to to -1. So you get 0.1, right? CL naught is 0.1.
Yeah.
So here, if you plug this in here, you need to find out alpha. So what was the CL for maximum range condition? What was the CL for maximum range condition? The previous question.
12.9.
Was it 12.9? Okay, I'll just go with that. The CL, not the ratio. What is the CL?
0.866, right?
1.29.
Ratio. The
1.29.
1.29 equal to CL naught with 0.1. CL upon D alpha is 0.1 into from this equation, what is alpha? Just solve this. What is alpha? Yes. Is this right?
11.9.
Yes, correct. Similarly, now do it for the minimum power condition. The same thing. The only change will be where in this equation, the only change will be where this is same. We need to find out the alpha at minimum power. DCL upon D alpha is same. CL is the only change, right? CL will be this 1.29 value. This will change. For minimum power, let's just do it. Minimum power condition. Power condition, it will be the same thing, right? CL equal to CL naught plus DCL upon D alpha into alpha. CL was what for the minimum power condition? $2.236. I'm not sure. What was the value?
$1.29.
1.29 was the previous case, right? This was 1.29. What was for?
2.236.
So it's equal to 0.1 plus 0.1 into alpha. So in this case, what is alpha?
11.9.
That was for the previous case, right? Previous case, you had 11.9 degrees.
2.2.
2.2. 2.2, how is it 2.2?
21.36.
21.
It's mistake. Yes, 21.
Yeah. Someone who said 11.9, are you clear? The previous case was 11.9. Now it is the different, that is minimum power condition. Is it clear now? Not sure who said that, but is it clear?
Yes, clear.
Excuse me, ma'am.
Yeah.
Ma'am, how did we get the value of this DCL by D alpha?
DCL by D alpha is given here. Lift curve slope of the wind. CL alpha.
Okay. Okay, ma'am. Okay.
This CL alpha is DCL upon D alpha, which is the lift curve slope. Okay. Slope.
Okay, ma'am.
Okay. Moving on. This just observe this graph for a while. It is the graph between CD and CL square. So your equation between CD, relation between CD and CL was what? The drag polar. What was the equation? CD equal to?
CD naught plus K CL square.
Okay. So the relation between CD and CL will be a linear equation, right? So with the y-intercept CD naught and slope K, right? So you can see that relation here. Yes?
Yes, ma'am.
Yes. Okay, so now they've asked you from this given graph, what is the value of CD naught? CD naught is the y-intercept of the straight line equation. What is the approximate?
0.011.
Exactly. 0.01. And similarly, what will be the slope? K. K. What is the value of K? Just take any 2 points, approximate value. Just take any 2 points and tell me. So I'm taking this point and this point, okay?
K is 1, ma'am.
K is? So I'll just do this. Okay?
Around 1.
K is
Is around 1.
I'll just take this point. So that will
K is
be
0.5.
it will be 0.5. It will be around 0.5, not 1. So I'm just taking these 2 points. I'll just show you how I've done it. So it's 0.02. I'm just taking the slope of the points. Okay, so 0.02 minus 0.011, which is the value here, right? Divided by 0.2 minus 0. This comes to, it's approximately 0.5. This comes to 0.045, right?
Yes.
0.045. Is everybody clear with this step? I've just taken the slope. Just take any 2 points and just taken the slope. Everyone's clear with that? It's 0.045, around that range.
Yes, ma'am.
Okay. So that was the next question. What is the value of K? Then they asked you, what is the angle of attack of the aircraft for maximum range condition? How will you do this? How will you do this? It's similar to the previous question. For maximum range condition, what was CL?
Ma'am, CL alpha into alpha minus CL is equals to 0, ma'am.
What did you say? CL alpha into?
Alpha.
Alpha minus
CL0.
alpha L is equals to 0, ma'am.
Okay. No, but where
We'll
does
get,
is equal
we'll
to?
get the value of CL, ma'am. CL.
You will get the value of CL, but they've asked you to find out this alpha, right?
Yes.
Okay. So prior to that, we need to find out what is CL. We need to know all these terms. So what is CL for a maximum range condition? CL for maximum range condition. Maximum range corresponds to minimum thrust required. Right? So what was the CL value for that? Root upon?
Under root CD naught by K.
So our CD naught was, how much was it? 0.011. 0.011 and K was 0.045. So this value comes to around 0.5, right?
Yes, ma'am. 0.49.
Somewhere there. Okay.
0.49.
0.49. Fine. So now what is the angle of attack? According to the relation that he has given, what is the angle of attack? You know CL alpha, you know this, you know this. What is alpha? CL minus CL naught. Naught is just this value. On CL alpha. CL is around 0.49. CL naught is just this multiplication. Is 0.098 on 0.098.
0.49.
6 degrees. 6 degrees.
How many? How many degrees?
6. 6, ma'am.
6. Okay, I haven't calculated it. I'm going with that answer. Has anybody got a different answer? Is everybody getting 6? I haven't calculated this.
I'm getting 4.
Okay, let me just calculate.
Almost 4.
Okay, yes, it's 4. How did you get 6? Whoever told me this? Around 4. The one who said 6, are you clear now? It's 4.
Yes, ma'am, got.
Yeah. So similarly, these are the equations that we use to come up with this. Similarly, can you do it for the maximum power condition? Follow the same steps. CL for maximum power is? What is the CL?
Under root 3 CD naught by K.
Under root 3 CD naught by K. So CD naught was 0.011 and K was 0.045. This comes to? Point
0.856.
Okay, 856. And then what was alpha? The equation that he said, alpha minus 0 equal to CL. So what is alpha? The similar steps that we followed last time.
CL minus
CL minus
CL 0
upon CL alpha. Okay, what is the value?
7.7.
Okay, giving it 7. Yeah, 7 is the right answer. 7 points. Is everybody getting this? Is there anyone who hasn't gotten the previous one or this one? Is everyone getting the 7 or the previous one? Is there any confusion?
No, ma'am.
No. Okay. Okay. So now this is an interesting question. If the leading edge of the wing is extended during takeoff, how will the stall angle get affected? Okay, let me just draw the cross section. So this is your typical airfoil cross section, and the airflow happens this way. Right? So initially I'd asked you what is alpha stall, right? Alpha stall is the angle at which, due to flow separation, the angle at which there is insufficient lift. So during takeoff, if you want to fly it at an alpha greater than alpha stall, what will you do?
Extend slat for the leading edge.
Yes. What does the slat do? It
increases the
angle, right?
increase.
So,
increases the stall.
I'm poor at this drawing, but it extends the leading edge, right? So what will the stall angle be after this?
Stall angle will be increased.
Stall angle will be increased. Why? Stall angle will be increased is right. It's increased. Why?
It will increase the camber and maintain the airflow attached to the airfoil.
Yes. The flow will remain attached for a larger range of angle of attack variations, right? Did everyone understand that?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So when the leading edge of the wing is extended, the stall angle is increased, allowing you to fly it at larger angles of attack without stalling, allowing you to take off at larger angles of attack. Next question, for the jet-powered civilian aircraft, the thrust to weight ratio in climb flight will be. It's a small derivation. So let's just draw the climb flight. So if it's climbing in this direction, your thrust is here. What is this force?
Drag.
Drag, ma'am.
Okay. And this is weight, and you have a perpendicular aerodynamic force component called lift. And this angle is the flight path angle. Is this the diagram for climb? Is this right?
Yes.
Yes. Now, can you tell me the equations of motion in the thrust direction? Equation of motion parallel to thrust. Is somebody pointed? Just a minute. Somebody has pointed out an error. Where was the minimum power condition? Rohan?
Ma'am, it was in the last question, ma'am. It was mentioned as max power condition. It should be min power condition.
Right. It should be minimum power. Thank you for spotting that. It should be minimum power, okay? Everyone, it should be minimum power. There is no
Yes,
maximum power condition, it's minimum power. You're right. Thank you. Okay, coming back to this equation, can you tell me the equation of motion parallel to thrust in that
T
direction?
minus D, T minus D minus W
Yes.
sine gamma.
Correct. So now let's proceed with derivation from here till we get thrust to weight. Okay. So T equals W sine gamma. Now divide throughout by weight. You get T by W equals D by W plus sine gamma. Now you have T by W. You're taking assumptions. Okay. So you're taking this to be 1 by W by D. So this is plus sine gamma. Now you know for a climb it is not lift equal to weight, but we're just assuming, we're taking assumption here. Drag plus sine gamma. Now this lift upon drag will be greater than 1, right? Yes? Do you agree?
Yes.
Yes,
What about
ma'am.
sine gamma? Will be less than 1. Yes?
Yes, ma'am.
Yes. So this overall term, this will be less than 1. This will also be less than 1. Right? So it will be we're making approximations, I agree, but it will be less than 1, right?
Ma'am, it can be both D. It should be option D, since the sum
How
of both can be greater than 1.
can it?
Ma'am, he meant to say that the option will be D, ma'am, because it can be possible
Okay, when you
that it
add
does.
it, right. Yes. Yes, that is right. Thank you for that. It can be both, yes. So I think that, yes, that brings us to the end of this session. Does anyone have any questions? Any questions in the entire lecture? Have you all done your assignments, both 1 and 2?
Only one presently.
Okay. The due date for the second one is also tomorrow, right?
Yes, ma'am.
Yes. Any questions? We were not supposed to discuss week 2 contents this time, but if you have any questions, any doubts, I think I'll be able to look into that. Any questions? What are you finding any difficulty in the assignments?
Yes, ma'am. I'm finding difficulty in finding the assignments.
Can you tell me where you're finding the difficulty? What part?
The actually this is my second class, okay, in the aircraft design course. So
Yes.
I was unable to find out from where I should get that assignments.
Are you able to solve it now?
No, ma'am. Actually, a little bit new for me. It's not my core area of learning.
Okay.
So I'm trying
Assignment
to.
1, were you able to do?
Yeah, I'm still not completed. Yes, still I'm trying.
If you have any questions, you can ask now, or any particular question that you want me to go over.
No, right now, no, ma'am. I'll definitely ask later.
Okay, you can put it up on the forum. We'll get back to you.
Yeah, sure.
Anyone else facing difficulty or any questions that you want clarified, even from assignment 2? assignment 2 has this weight fraction. Are you all familiar with that term? I think the last couple of questions have this weight fraction.
No, ma'am. Can you please brief us about it?
Okay, so the question, what does it say? So initially, it says it loses. Let me just look at that question. Just give me a while. Just give me a few seconds, okay? Okay, so let me just share my screen. Is this the one? No, it's not one. This is your assignment 2. Here, the last 2 questions have this thing known as, so weight fraction. So in this case, what we do is, I cannot write here. Did you go through this question? I'll just go to the PowerPoint to write. So I can write here. So weight fraction at the end of the flight is final weight by overall weight. So this they have given you as 0.85. So initially, what would this ratio be at the beginning of the flight? Weight final is because it has lost some fuel, right? So it's this minus some fuel consumed. So this is the final weight. So initially, what would this ratio be?
It would be 1, ma'am.
It would be 1. So the first ratio, ratio 1 would be 1. Ratio 2 is 0.85. So I cannot completely solve this for you, but you're getting an idea. So that is the weight fraction, the ratio of the weights. So in the final state, it is weight final by weight initial. In the initial state, it will be weight initial by weight initial, right? So that is 1. And the final fraction is given to you here. And they've asked you what? How much fuel is consumed. The only change between weight of the fuel consumed is weight initial minus the weight final. Minus weight final, right? If you subtract these 2, you should be able to get it. I cannot completely solve this before the assignment is due. So I hope you get an idea. The next question is again similar to that. They have given you the fuel weight fraction, how much fuel is consumed. Did you get some idea? We will obviously discuss this next session once you have submitted the assignment, but I hope I am able to.
Ma'am,
Yes.
ma'am, can you explain the graph in the previous question, the just above?
1 second. Okay, so this is the power required versus velocity graph. If I explain it right now, it's going to give you the answer right away. You have studied the power required and the power available graphs, right? So you studied this power required. Have you taken the previous course, aircraft performance?
No.
No.
So that is a prerequisite to this course. Okay. So there is this power required versus power available graph. So power available is something like this. And the first question I think is fairly simple, right? So they've asked you for what this point suggests. This point is the least value that this graph attains. The next point, I'm not sure how I can tell you without just directly giving you the answer. We'll discuss this in the next week. Okay, just look into this power required graphs, look it up in the books that are mentioned, or just Google it. This graph would be there.
Ma'am?
Or yes,
Have a little bit doubt in first assignment also, ma'am.
first assignment. Let me get to that. Okay, where did you have a question?
The Epler series, ma'am, in some down course. About Epler series, yes, ma'am. These airfoils. And not much information is given online about them.
Okay, so have you studied the NACA airfoil series? You know
Yes,
what
ma'am.
each component, you know what they represent, right?
Yes, ma'am. That will.
So given that, won't you be able to get this, what it stands for? No?
Ma'am, for 4 digit we can get, but for 3 digit really don't.
Okay. We'll have to discuss this in the next week. I cannot tell you right now.
Okay, ma'am, no problem.
Uh,
Also, on the answer of V stall question, it is above. Third, fourth question. No, this fourth one.
Fourth
Ma'am,
one.
here the answer is given directly V stall square. Answers are pretty big. I mean, they are V stall square, but the question is asking for V stall only. So,
Okay.
so I think I have to mark the square. The
Are you
stall
sure? Are
square.
you sure
Yes,
it's
ma'am.
square?
Yes, ma'am. The answer is given in V stall square.
Okay, then go ahead with that. I will check up with the other TA.
Sure.
But just go ahead with the squared values then. If you're getting that, just check once again. But if not, I'll verify with the TA who has assigned the assignments.
Yes, sure, ma'am.
Okay, I'll just note that. Yeah. Thank you for that. Anything else? The questions
ma'am.
discussed today are fine, right?
Yes, ma'am.
Okay. Does anyone have any other questions? Okay, if you have any questions, put it up on the forum. We will try to get back to them as soon as possible. If you don't have any other questions, I think we'll end the session today. Yes.
Ma'am, I'm having a doubt, ma'am.
Yes, please ask.
Ma'am, you showed a slide, no, ma'am, in which it was showed the contribution made by the wing and the tail, ma'am.
Yes, I'll just get to that slide. Yes, this one.
Yeah, yes, ma'am.
Yeah.
Yes, ma'am, this one.
Yes, what was your question?
Ma'am, ma'am, I was actually having a doubt on this entire thing, ma'am, because I didn't learn this.
Okay. All right. So stability control is actually a prerequisite for this course, but I'll try to explain it to you. So this is your aircraft where this is, okay, I'm just drawing a straight line. Okay, so your wing is here. This is the aerodynamic center. You understand aerodynamic center, CG, all that, right? Achyut? Achyut? Can you hear me? Can you just type in the box if, okay, there is a,
Ma'am, actually, voice is breaking, ma'am. That's why I couldn't able to understand.
okay, yeah, sure. Are you familiar with aerodynamic center, CG and all of those terms?
Yes, ma'am. I'm familiar with them, ma'am.
Okay, so so for a typical aircraft, so your aerodynamic center of the wing is at the quarter chord point of the airfoil cross section of the wing. Similarly for the tail. So now, how do I explain? So the wing contribution towards static stability. Do you know what is longitudinal static stability? It is the ability. So if your aircraft is flying at some value, at some pitch value, at some angle of attack, and it's subject to some disturbance, and you want it to come back to your equilibrium. So it should have a pitch down moment, right?
Yes, ma'am.
Yes. So the ability of the aircraft to pitch down is called longitudinal static stability. What is the quantitative measure for that? Is that Cm alpha, dCm upon d alpha should be less than 0. Now, if your wing CG is above, so if now your angle of attack is here. Now it is subject to some disturbance and this angle of attack increases. Your aircraft, this entire fuselage reference line goes above. It becomes like this, okay? And you want it to pitch down. So there is, what are the forces that are acting? You have lift on the wing, you have lift on the tail, right? So this lift on the wing will produce what kind of moment about CG? Pitch up, right? Nose up. Yes?
Yes, ma'am.
Yes. So it doesn't contribute towards stability. It is, if disturbance is in pitch up direction and it's continuing to give a pitch up moment, it is adverse effect. It's not contributing towards stability. But tail gives you a pitch down moment about CG. So tail is contributing towards stability, right?
Yes, ma'am.
So this is the major idea given in these equations. So let's ignore this y-intercept part, that is ignore the Cm naught part for now. Let's just look into Cm alpha part. Now the Cm alpha part shows you that the CL alpha is positive for any airfoil, it is positive, the slope. This value is negative, which is why it gives you this pitch up moment. That is adverse moment. It doesn't counter the disturbance. So this entire Cm alpha is positive, which does not give you negative Cm alpha, hence it is not stable. Okay. But for the tail, this entire term, including this negative sign, it becomes negative, which is again seen from this graph, from this figure, that it contributes towards a restoring moment. Right? So according to equations, this is greater than 0, so it is not contributing towards stability. This is less than 0, so it's contributing towards stability. These are the main implications of these equations.
Okay, ma'am, but here the minus signature will not lead to positive, ma'am.
Which one? Tail contribution?
Yes.
Yes. So this term is negative. Do you agree?
Yes, ma'am.
So this term, sorry, my bad. This term is not negative. This term is just the moment arm. It's this length. It's this length, the magnitude of the length. That is the moment arm. Right? So this value is greater than 0. Do you agree?
VH, ma'am.
VH is greater than 0. Yes?
Okay, ma'am.
Are you able to understand why it is greater than 0? This is the area, this is the area, this is the chord, and this is the moment arm, the magnitude, not the direction, the magnitude of the moment arm, this distance.
Okay, ma'am.
Yeah, so VH is positive. This tail efficiency factor is the ratio of the velocities, again positive. CL alpha,
Okay,
lift slope of tail, again positive. This value, this dou epsilon upon dou alpha, the downwash slope is always less than 1. Right? The slope is less than 1. So this entire term is again positive. So this term is positive, and since you have a negative sign, Cm alpha contribution of the tail is negative. Yes?
Yes, ma'am.
Yes. So it contributes towards longitudinal static stability.
Okay, ma'am.
Is that clear?
Yes, ma'am. It's clear, ma'am. So, ma'am, what is here actually x, ma'am?
X, where is X here?
Ma'am, xcg minus
Just the
x
distance. It's just so if you take any reference point, any reference or plane, and the distance from that plane to those given points, that is given aerodynamic center of the wing, aerodynamic center of the tail, and CG, that distance is X.
Okay, ma'am. I understood, ma'am.
Okay.
Just for a second, can I take screenshot, ma'am?
Yeah, I will be uploading these slides, but you can take screenshot, yes.
Thank you, ma'am.
Sure. Anybody else has any other questions?
Ma'am, one more thing, ma'am. The previous two courses are there, right, ma'am?
Yes.
So how can we get hold of those videos, ma'am? Because the thing is that I started this course from the last, ma'am. Before
Okay.
2 months, I didn't started, ma'am. So how should I get to know about those two courses, ma'am?
Okay, just a minute. Are those videos not available on NPTEL?
No, ma'am.
Okay, let me just try to find it out. Give me a minute. I thought they were available. We'll just share the link of the course. You just have to Google aircraft performance on NPTEL and then you will get it. Yes, somebody has shared the this is aircraft performance. You have stability control. These are the links to the previous courses. I think it should help you with it. Have you gotten the links?
Yes, ma'am. I got them, ma'am. I'll go and save them right now.
Okay, yeah. Rohan has sent a message. Can you just elaborate that if you're fine with speaking?
Ma'am, this is with respect to the last question, ma'am. So for a civilian jet with weight which will approximately be say 30-40 tons, having an engine which will produce thrust greater than weight will be very difficult. Though it is possible, like in a lot of fighters, it is still possible to have thrust more than weight. For a civilian aircraft, it might be difficult to find an engine which will actually be able to give thrust more than weight.
So you mean to say that it will always be less than 1, right?
Ma'am, as a practical consideration, yes.
Yeah, so thrust by weight will always be less than 1 is what I had also understood, but I'm not able to justify it from the equation. From the equation, it seems that the last option is right. Let me just share it again. If anybody is able to find any mistake, just do let me know. The last slide, right? It's this one. I'm not able to justify it from the given equations.
Ma'am, actually, if thrust is more than weight, then you can do a true vertical climb in which sine gamma will be 90, sine gamma will be 1, or gamma will be at 90 degrees. So if barring that one condition, it is very difficult to get thrust more than weight, or practically have an engine which will
Practically,
work
yes, I understand.
because
So
if thrust is more than weight, gamma will be 90.
yes,
So barring that one
that
condition,
will not happen for civilian aircraft. Yes. Okay. So even I believe that the right answer is it's. So this is wrong, and I believe it is this. I will just look into it and get back to you in the next session. But yes, I do believe that it should be less than 1. You are right. I will try to justify this answer in the next session. Is that all right?
yes, ma'am.
Any other questions? Okay, if not, we'll end this session here. Any other questions, please do post on the forum. If nothing else, then we'll stop here. Thank you. We'll meet again next week.
Thank you, ma'am. Thank you very much.